Welcome back to the second part of our tutorial on autonomous smart contracts on the Massa blockchain. In the previous video, we introduced the basics of creating and deploying smart contracts. Now we'll dive deeper into two powerful features: async call, used for lightweight, non-guaranteed execution, and deferred call, which ensures reliable, guaranteed execution of future tasks. We'll see how and when to use each one, along with concrete examples. Let's continue. Let's level up to autonomous smart contracts that can trigger actions by themselves. We go to the async call project. This is basically the same structure as we have seen on the directory assembly and the directory src. Assembly contains the main code of the contracts. We can have a look at it. This is very similar to the code we have seen previously. So I will focus only on the specific part, which is the function async hello. The function async hello starts by generating an event just for us to see it's live. Next, it gets the current period and thread. It computes a new target slot with this one. It does an async call to itself with two parameters that are a time in the future. We will respect the Massa time when it wants the call to be triggered. Next, it prints another message telling us at what time we can expect the message. Basically, in the src directory, we find nearly the same thing. The deploy script is the same as before. The function call this time is a bit different, not that different in fact. We will use it to trigger the first asynchronous call. This call could have been done automatically inside the constructor of the smart contract. But for the purpose of this video and for the simplicity to follow, it is triggered by hand. So we trigger async hello message. It's simply a call like we have seen in the Hello World example. Nothing fancy here. We can have a look at the listen script, which will help us to monitor events automatically triggered by the smart contract. So it's basically a script that awaits for events emitted by the smart contract and simply puts a console.log. So let's move to the directory. Let's install the dependencies for this project. Now let's build the binary of the smart contract. We can deploy it on the blockchain. But first I will copy the .env file from the Hello World example we did in the first video and just remove the smart contract address. I can now run deploy. Okay, so our new smart contract has been deployed. I can now take its address and put it in the .env file. We are going to open a second terminal. What we can do is run the listen script. Okay, so in the script, as I said before, this script monitors for any event emitted by our smart contract. So the first and sole event for the moment is the event emitted by the constructor. And on this terminal, we can trigger the asynchronous call. So here we see that the async hello function has been called successfully. We wait for the operation to be finalized. In parallel, we can see the call we have made with this script. That has generated an event. Okay, so our script has finished. And during this time, we can see that another async call has been executed. We can wait a little bit for the next one to happen. And for now, the smart contract will call itself periodically without any external operation. Okay, we have seen another one. And as this contract is very simple, as long as there is no problem, this event will keep being triggered. It will never stop until the contract has no money. An important thing to note here is that async calls are simple and cheap, but the execution of async calls is not guaranteed. Such a call may fail if, for example, the async pool of execution, this is a pool where any async operations are stored, gets saturated. For example, one can think of an async call like what UDP packets are in a network. They are cheap and fast, but may be lost or delayed. To improve reliability, let's explore what are called deferred calls, a mechanism that offers guaranteed execution on the Massa blockchain. We'll now move on to the last example of the day. First, we copy the .env file and just remove the smart contract address. Then we take a look at the code. The project structure remains the same as in previous examples. As usual, the smart contract code is located in the assembly contracts directory. This particular contract has a very simple structure and interface. It includes a constructor and two exported functions. The first one, getNextCallID, allows monitoring of any ongoing deferred call. The second one, stop, provides a way to cancel a deferred call that has already been registered. In the constructor, as mentioned earlier, we can register a deferred call automatically. This is done by invoking the register call function. Let's look into it more closely. The register call function starts by checking the balance of the smart contract. It then sets a few parameters, especially the maximum amount of gas we're willing to spend. After that, it begins by finding the cheapest slot in the future, during which the call can be executed, based on the specified period, gas requirements, and parameter size. Using this information, the function deferred call quote can estimate the cost of the future execution in Massa coins. Finally, we use the register call function to actually schedule the call. We specify the address, which in this case is the contract itself, the method to be called, the chosen execution slot, the maximum gas allowed, and the input parameters. At the end of the process, we compute the booking cost, and this cost is added to the event that confirms the registration of the deferred call. In summary, the way to guarantee asynchronous execution on Massa is by pre-booking an execution slot in the future. This mechanism ensures that, once scheduled, the call will definitely be executed. One interesting function here is process task. This is the function we call asynchronously. It retrieves the task ID and determines what kind of work needs to be done, whether that's emitting events or storing information on-chain. At the end of its execution, the function reschedules itself, setting up another deferred call to ensure continuous execution. We also have a function to cancel or stop this mechanism if needed. That covers the core logic of this smart contract. Now, like with previous examples, we take a look in the src directory where some new scripts have been added. We'll use them to deploy the contract and listen to events. The deploy script works the same as before, and the listen script will monitor events emitted by the smart contract. Let's run it. We start by deploying our smart contract. Once deployed, we copy the address into the .env file. Now we can monitor the first event emitted by the smart contract. As expected, we can observe the booking cost being emitted. Then we take a look at the contract's history. We use the listen script again, and we now start seeing all the events emitted by the smart contract. We also notice that the contract's balance decreases slightly each time a new execution slot is booked. This confirms that the contract is autonomously scheduling tasks for future execution. We can wait a bit for the last scheduled execution to take place, which will happen in just a few seconds. That's it. To recap, we've seen everything from setting up the environment to building and deploying simple and autonomous smart contracts, and finally, contracts with guaranteed execution through deferred calls. You'll find all the useful links in the video description. If this guide helped you, don't forget to like and subscribe. See you in the next one.